Christine, Michelle, Sam. Good morning, good afternoon to some of you, maybe even good evening. Tell us in the chat where you're tuning in from. I'm currently tuning in from Stockholm, Sweden. Eric, where are you coming from?
Gothenburg, Sweden.
Is that the West Coast, right?
West Coast. Yeah, West Coast. Unfortunately, not as windy as I like, because I like the windy days right now. It's my favorite weather.
But no rain? Sideways rain?
Rain, no sideways rain, high winds. I also want to take that world record in model airplane flying. My aim. That's why all of a sudden high winds is my favorite weather.
Mm-hmm.
Yeah.
Also for idea generation. Let the many ideas fly and float.
Perfect.
I've been enjoying the snow days in Stockholm.
Yeah, we had a couple of nice snow days, and especially what was most nice was the ice skating on all the small frozen lakes around Gothenburg, which is pretty rare for Gothenburg. So that's been a quite nice little view. I enjoy it. So I haven't picked out my skates yet, though. Even though I used to play the Swedish version of hockey. I don't know if anybody out there in the world knows this, but it's called bandy.
Bandy.
A round ball and a curved club, and you. Yeah, it's very rare that people know about it. It's like Sweden, Russia, and Finland. So, but Gothenburg, they don't have many bandy teams, so that's not going to be a career move.
I'm sure there's quite a few in Stockholm, although I've never heard of it until just now.
Stockholm and Uppsala, Hammarby is in Stockholm.
I see someone is tuning in from Argentina, although it says cold most of the year, or part of the year as well.
Yeah. Oh. Yeah, Gothenburg is mostly known for like windy and rainy, not so much snowy.
Mm-hmm.
But I like that. So.
Well, I mean, you kind of get used to the fine art of rain. You know, like rainstorms will not make you stay indoors.
No.
You have to embrace it.
Yep. Okay. Let's see. I got my notes.
Okay, we'll just get started in 1 minute.
There is a question as well. Perhaps you, Eric, want to quickly respond to that. Christine is asking, like, that here in Canada has Kids 2030 challenge on plastics. I know that using strawberries is different from single-use plastics, but what is the best way to explain this in an environmental friendly way? I know you've got an environmental degree and a mechanical engineering degree, so you're probably the right one to answer a little bit more. Also to kids.
Yeah, exactly. And we're making a statement on this, because so obviously from my point of view, with that degree, to actually use plastic in a good way is one of the best ways of reducing carbon dioxide, and actually it's a very tricky thing. What I'm looking at material flows rather than just one particular material. How do we actually make sustainable material flows? And that's where my degree was actually focused on, trying to get it circular. And obviously that's not super easy, but you have to figure out how to make the most of the least amount of material in a way. And that's actually a very good example of what Strawberries is doing. And especially because the material is very durable if you compare it to the weight of the material. So you will have it working for a long time. But then we also need to,
Oh, I think we just lost you for a second here. That's the office internet, right? Oh,
Yep.
yeah. But I'm going to post also a link to you guys into the chat about Eric's explanation about circular economy. Oh, you're back.
Okay. We'll just wait a second for Eric to return and then we'll get started. All right. Well, while we wait for Eric to rejoin us, so thanks everyone for joining us for this version's Strawbee's PLAYINAR Do Your Bit. So it's a partnership with Microbit Foundation. So we're really excited this year to participate as a proud partner, as one of the delivery partners for Do Your Bit competition. So some of you may be new to the challenge. Some of you may have entered the previous years, and we're excited for the first year to be joining in the session. So my name is Lindsay, and some of you that may know me, I am on the education team, head of education here at Strawbees. And with me is Vivian. Vivian, can you just wave? Hello, hello. And Eric Thorstensen, he will be helping us go through the session today. He might just tune in a little bit later. So, today I'm going to send, so usually in previous PLAYINARs, what we do is we have like a very interactive session, which we always will try to encourage during our PLAYINAR sessions. But we also will have like a short presentation about what is Do Your Bit, especially for those of you that maybe are unfamiliar with the challenge, as well as how to enter and roughly the different categories, and just a little bit about the Sustainable Development Goals, a little information about these global goals that we are solving challenges and providing solutions for. So, and usually during a PLAYINAR, I slowly send in resources, but this time I'm going to be sending resources right now in the chat. So, I'm going to be very transparent and share my presentation slides as early as possible. But at the very end of the list, there is a massive list of links and resources for you. So pointing at different activities on Microbit's platform, as well as on Strawbees Learning and on our website. So that way we can have all the links at once and not have to worry so much about trying to find them. So Eric has just joined us. Hello, hello. You are muted, my friend.
Me?
Yes, now you. So Eric, can you introduce yourself to our fellow educators?
Yeah. So how long do I have? We haven't been talking about this yet.
You have like about 1 minute, 2 minutes.
One minute,
a brief intro.
Okay, my name is Eric Thorstensen. Now I actually have an extra name because I got married, so I'm not used to it. Erik Thorstensen Boye. But anyway, I am a mechanical engineer. That's my background. I've been talking and playing with technology for a long time. I had a 3D printer when I was 18, 19 due to my, we got one in my school, and that's a long time ago, 98, 99. So anyway, I've been playing with that kind of stuff for a long time. I wanted to build airplanes, but I got sidetracked by industrial design and solving problems. And I thought that was incredibly fun. So I started my own little business pretty early, immediately after university. So I've been doing things, and the big thing that I did back then when I studied was studying how to make products in the most sustainable is a tricky term, but most future-proof way possible. So we were looking at material flows, energy use, and trying to see how long, and all of this has to be done in comparison to how long the product you make is used by the end consumer also. So there's always a balance. We can make it last for 100 years, but the user uses it for half year, then it's really redundant, like it's a waste of material in a way, unless it gets on. But anyway, that's what I've been doing. I don't know if that explains anything, but I do a lot of, I like playing with ideas, and I have a pretty big creative confidence, at least, which is something that I want to pay forward. So that's actually the project Strawbees, how it began. I don't know if that says anything, but
no, that's a great intro.
That's who I am, I think.
Yes. And we also have a website for sustainability, strawbees.com/sustainability. If you have more information, if you want more information on sustainable tinkering and reduce, reuse, and recycle concepts. Okay.
Something.
So now I'm going to go ahead and just do a short presentation on Do Your Bit. So see here. Excellent, excellent. So a little bit about Do Your Bit. So this is a microbit digital challenge for the global goals. So there's a lot of information that you can find on the main website, microbit.org/project/doyourbit. So I highly recommend getting all of your information about the terms and conditions, how to enter, and kind of the ideas, and also even activities that you can find on Microbit's website. So again, we mentioned that we are a very proud partner of Microbit. So, you know, the Microbit challenge is for ages 8 to 18, and participants can, you know, enter on their own or as part of a team. So if you're on a team, you can have up to 3 members. And there are actually now 2 age categories, ages 8 to 14 and 15 to 18 years old. So on the website, there's actually different ways that you can enter, from sending the original hex code, you know, creating an actual solution with using Microbit, Strawbees, cardboard, you know, any sort of like design that you come up with that you can prototype with like physical materials and take like a video and send it in. And there's also for specifically for the ages 8 to 14 category, you can even submit a prototype using paper. So you can use like a drawing and kind of draw. So even if you don't have the Microbit at home, it doesn't actually necessarily discourage you from still participating. So if you're a very passionate prototyping engineer, have a lot of great ideas, you can even make drawings. And actually for myself, drawing is something that I really enjoy doing. So I think actually my personal favorite is to show the drawing process of, you know, idea formulating. So, you know, the global goals. So I just want to talk a little bit about what the global goals are. So the Sustainable Development Goals is basically a blueprint designed by the United Nations for Agenda 2030. So the idea is that we want to reach a more sustainable, well-rounded Earth globally amongst all countries in unity, trying to achieve the 17 different global goals. So the global goals are fairly flexible. So you have some like on no poverty, you want to have reduced inequalities, so more equality for all. Coming up with responsible consumption and production, which is something that at Strawbees we really like to highlight about sustainable tinkering. Reduce, reuse, recycle, redo. And then climate action, as well as life on land and partnerships for the goals. So it's really important that collaboration is something that we really highlight. So in this planar, hopefully I can share more with Eric Thorstensen and I, where we're going to do a little bit of pair programming. So we're going to actually do a little bit of collaborative play with some of the activities that we have on Strawbees Learning. So that way it can kind of inspire you to create your own inventions. So a lot of the ideas we have are going to be very flexible, but not necessarily, you know, just like a few ideas of different solutions that Eric has actually managed to come up with through the School of Ridiculous Inventions. So I want to actually try to inquire this creative learning process, this process of how to come up with an idea and how to implement the idea. So, you know, as part of the challenge for Do Your Bit, basically, in very basic terms, it's design a solution to a problem that affects you and your community, or another community somewhere in the world, delivering the global goals using Microbit. That's kind of the simplified version of the challenge. And this year's challenge is focusing on 2 global goals. Number 3, good health and well-being, And number 13, climate action. So while we also want to, when you kind of create your inventions, you can also think about applying it to to other global goals. So trying to achieve global goal 3 with good health and well-being, as well as gender equality, clean water and sanitation. So we encourage you to, not just like think about one of the global goals, but even considering even combining good health and climate action together, but then also considering that you can look at other global goals as part of the process. But ideally this year, the challenge is primarily to create solutions with global goal 3 and global goal 13. So you can find more information on microbit.com or microbit.org and the project's Do Your Bit challenge, as well as on learning.strawbees.com/SDGs. So I want to talk a little bit about, the 2 global goals that is part of this year's challenge. So good health and well-being. So the very basic definition around this, we're not so much a definition, but more so a statement of what we want to achieve, is to ensure healthy lives and to promote well-being for all ages. And so now it's like, now we have something that's very, almost like the challenge is, like, how can we kind of approach this challenge? So taking this global goal, what are solutions that we can design revolving around this challenge? So we kind of create a few questions and broke it down a little bit more to really help you provide this information to your students as you guide them through the Do Your Bit challenge. So, we wanted to repose the question as how can we reimagine a society where everyone can have and maintain good physical health, but also support mental wellness? Because sometimes mental health is something we actually don't think about as much. And I think that is actually a fairly main point to bring up in, recognizing what is good health: mental, emotional, and physical health. So we provided so now if we break it down a little bit more into thinking about what are ways that we can explore good health and well-being is, here's a few open-ended challenges to get started. So a way to access clean water, thinking about that some individuals don't have access to clean water or lack filtration systems. So what can you create to provide access to water, or for somebody that has to travel a far distance? So making it very accessible. Invent something to prevent or spread a virus. So I'm sure we can all understand that COVID-19 has been, something we've had to deal with as a real world problem. So what are solutions you can create to prevent or spread the virus? Also thinking about ways to exercise and play during a pandemic. So since many of us have to quarantine at home, how can you stay in physical shape without having to go outside? What are ways that you can, keep your body fit and healthy and happy? And then also to make an emotional support invention for a friend. So maybe some of us might start to feel, as we quarantine, a little depressed, maybe anxious, or we don't have many, or we just lack a lot of social, so we feel very lonely. So providing a solution for individuals that perhaps need a little bit of, tender, loving care at home. So, and then also the last one is to create something accessibility inventions for citizens, or to create something for accessibility citizens, excuse me. So what are ways that you can, redesign your home or around a city for someone that is in a wheelchair, or someone that, has, maybe they can't pick up, maybe they can't bend over and grab something that falls on the floor, or something that falls behind the couch. So these are kind of like ideas to really open and broaden ways that you can design and invent different things. And then climate action. So global goal 13, climate action, to take urgent action to combat climate change and its impacts. So we wanted to pose this as the question: how can we reimagine society for a safer and more sustainable future for citizens? So if you're thinking about even like a very densely populated area, like a city with a lot of people, maybe you live in a more rural town, but you do have, maybe you might have a few densely populated areas like the grocery store that everybody goes to. So suddenly that's the one area that has a lot of cars. Thinking about the effects of climate change and how it affects like weather and how it can actually inquire more natural hazards in some areas. So some areas of the world might be more susceptible to flooding, hurricanes. So how can we, create a society that's safer for citizens as the climate changes? So, now even breaking it down further, thinking about, creating solutions or inventions for, reimagining transportation. So maybe making transportation that is more publicly accessible. Also thinking about maybe low emissions transportation alternatives. Designing a way to reduce damage from a natural hazard. So some natural hazards like flooding, how can we prevent flooding from overtaking like areas that have a very low, that are really close below sea level, smaller on islands or in areas that maybe are housing that's right next to the ocean. Thinking about something you can invent to protect animal habitats and maintain biodiversity. So some animals like amphibians, if there was a if as the world starts to get hotter and hotter, amphibians might be the first one to actually be affected, as well as in the North Pole. You might the glaciers are melting, so perhaps you want to think about more maintaining habitats for polar bears. So these are different applications that you can think about inventing with microbit with. So, and then also the last one, create a way to sustain food crops for continuous food security globally. So again, as we inquire like warmer climates, there is actually a higher risk of droughts as well. And maybe food crops may not be as plentiful as years go by. So how can we ensure that we have enough food for the future in case a major drought comes through? So, I just wanted to take the moment to, really expand and really dive deep into the sustainable development goals a little bit. So, really thinking about what you want to create. And now I'm going to take you a little bit through a design process. So, now I'm going to kind of turn it up to Eric Thorstensen here. So Eric, hello.
Hello. Now,
Hello.
I hope my internet stays now. I've had serious issues here in Gothenburg. I don't know what's happened. It's been diving. So I hope I'll stay in tune with you guys.
Yeah. Well, let's try it.
Yeah.
So, you had a creation that you made before this session. Can you share it? It was actually something you created for good health and wellness, Global Goal 3.
We've been doing that. I have actually, it's something that I keep close at heart because it's actually pretty tricky to talk about these issues. It's a way of getting past that first trickiness of if you sit down with the class and talk about your feelings, it's a bit harder. But if you, for example, talk about a robot's feelings and what kind of states it can have, it's easier to get started with this discussion because what you're actually doing and what they're discussing is different states of how can I feel? And discussing that in the context of a robot has apparently been easier, which is what I've been using to unlock it. So I call those things our empathy robots because I'll show you one down here. Because the first thing they need to analyze is what kind of feelings can I feel and what is what are the signals from me when I feel a certain way, for example, calm or stressed, etc. So, and that's been something that's very inspirational. It's also easy to talk about when it comes to making this robot make you feel like it feels something. That's what we call about the empathy aspect of this. And that's about mental health because from sidetrack, but then we actually can make these, for example, companion robots immediately when you see this and start seeing if it can read you and how you're feeling, it can actually respond to that a bit, and that can be comforting in a way. And I'm going to show you the project. Sorry for talking and showing myself, but I'm going to show a simple version of the innovation process around this. So I'm going to see if I can shift to my other camera. That's going down on the floor. He's flickering a bit, but do you see this? the little robot on the ground. I'll come down here and show. So this is not the robot I'm showing, but here he is. This is an example of an empathy robot. And he's not on, or he, she, non-gender actually. See if I can get him into the camera here. So I'll turn this robot on. This is has a, now it's going to be tricky because I'm using the latest microbit with this, but this is a version 2 microbit in here. The first thing we do is a calm heartbeat for the robot. So then they measure that. So they actually do the science first on themselves to measure, okay, what's a calm state? Like I'm not agitated or in any way. And actually now the robot, I'll put him down gently. Now the robot responds to sound, for example. So, and now it's actually a happy robot. So it reacts to people being there. Hi! And it gets happy and elated, and the pulse increases and it waves to you and makes little springy noises. So that's a simple interaction where it realizes that somebody's there through sound. Hello! And he reacts. So I made that for, like, I've been playing around with these types of simple robots. And right now you can see it is a happy robot. I'm coming in with my face and I'm like, hi. But it's very easy to make this an angry robot because there's very similar responses. So if you talk about this, there's a very similar response if you're angry. So the only thing we need to do is to make it is the angry neighbor. So this is about how to become innovative or creative. It's about shifting perspective or the story around the object. So now you see it looks a bit more angry, doesn't it? It's a non-content robot. And now if you make a sound, it's getting angry, looking at you and trying to make you not make sounds anymore because it wants to be calm and quiet and sit there and sulk for a bit. But I mean, so the innovation and the story in these things are actually quite a lot in the story rather than in just the code, for example. So there's a combination of making that story work or the robot react the way you want it to through your code. And then you can make this more and more advanced. So another thing we did, so this starts the empathy robots and many different versions of them. And my wife tells me, please make more happy robots because happiness is needed. But for me, it's very interesting to see how people react immediately to, for example, making it shake. So it's afraid or frozen. That evokes a much bigger reaction than for example, the happiness part actually in a way, because they don't really see that, but you feel bad for somebody much easier. I don't know if this is a territory you want to go into, but it's very interesting because that's much deeper in us and they want to cover it up. So for example, we use the light sensors. Like if you want to be creative, for example, with these mental health robots or whatever this could be, you can look at different stories and different ways we actually react to things. But one thing, like if somebody gets stressed, you can actually look at what you actually should do and replicate that with a robot. For example, one really good way is if somebody has you could have an anxiety attack, to make them actually warm, just cover them or hug or whatever that is. You never know which reaction, but first thing, just cover with a blanket or something. We can read that with the light sensor on the microbit or the whatever robotic kit you use. And we can read that they're being covered. We don't even use a temperature sensor. We could also use a temperature sensors, things like that. But that's a way of being creative with the assets you have in the circuit board and then actually solving something that you feel like it's reacting to you and your actions. And I really enjoy that type of invention and innovation. And you get surprised about the creativity they use. If you can just give them this simple program and they're going to tweak it and it's going to be amazing in a way. And then some will try to move the eyes because that also reacts quite a lot. And then you have to make some little linkages to make the eyes move. And I'm all for that too. We've even started doing with the single servo motor, you can also do paper pop-ups. I don't have anything to show here, but all the classic pop-up books, which is another fascination of mine, are very easy to replicate with this robot. You just pull one of the papers or fold up a paper and then it starts moving. And we can use that for eyes or for other reactive elements. So that's yeah, I don't know, that's just the beginning. It's one of the ways I really like talking about it. And then what happens is when you play around with this, every failure, if you wanted to make it look happy, for example, and you realize that what happens when you laugh, Lindsay?
I smile and I get really excited. I shake my hands.
Yeah, you shake your hands. Other things can, when you get really, really happy,
I laugh.
yeah, you laugh. And what happens with your body? So we're doing the analysis now. What
Yeah.
do we want to replicate with a robot? And that the laughter is a fun thing. So you, for example, trying to replicate laughter in the robot, we can use the sound, but because it has a very limited sound, the new one, you could obviously throw out samples of laughter, but you could also make this shaking motion. And if you want to get the right shake, like there's different shaking motions. So this is a chuckle. And then you have a, it's better. You need a tilt and a big shake. Then trying to make that with your servo is amazingly fun, and you won't succeed in the beginning, but every failure becomes something that actually evokes an emotion in you. For example, oh, this looks like it's really, really sad, or this it's not in a good mental state. Because they're very close to each other, all these things, but every failure or attempt at evoking one emotion with an empathy robot actually can give you a track for a completely different area. So then you just put that in your notebook, stressed robot or or other mental health, put that in your notebook, and then you can use that for later. And it's a very interesting presentation because everything will evoke something. You will see that it happens. Like a very monotonous motion is very, very scary. If it just does this and you're supposed to react to emotion, it can be very strange. So yeah, that's one way of playing around with the mental health issue, which is a very important thing, especially nowadays. So knowing that and actually being able to read your own signs, we're doing it, discovering it through robots, and the robots can only solve that much. But we've actually seen research showing that companion robots can actually work. Anything that can react to you and respond in a good way. I have a friend who made, I don't know if you've seen the little cat pillow. That's just a pillow with the tail on.
No, I have not seen it.
That's a typical empathy robot that actually has been shown to work. So you pet that little pillow that's furry and fluffy, and it has a technical tail. But what it does, it responds the way that a cat would if you can't have a cat, which a lot of people can't have. But they have a very calming effect. So it starts purring and it's reacting positively to your interaction with it. That makes you feel better. And then you're in this interesting loop of feelings. So that it's something you can check out. It's from Japan, of course, but I do believe it actually has some of these things can feel like they're gimmicky or just fun, but it becomes something that's actually important. Yeah.
I think that this kind of starts to go into our next part of the process. So, I think with like idea generation, like sometimes like looking around what's your house, what you have, as well as things that you want to improve, maybe even looking globally, but even just having a conversation, talking about it, and even describing it, which is kind of like pseudo coding, wouldn't you say? So
Yeah.
like to make that empathy robot, it didn't just kind of come out of nowhere, which I think is a very important aspect that we want to, teach teachers about. That how do we take an idea and transform it into a working prototype, but also that can be, translated into something that can be used for good, or like basically to innovate off of or to improve, especially these very large issues we have with the global goals.
Yeah, and obviously, as you were into some things that are very important, like you can start problem solving or innovation. There's so many avenues to approach this through, but for what we need to start practicing is actually how to implement or prototype an idea, like how to actually see or how you trying to find the word here, to actually find or identify a problem. And that can be identified through frustration and just, or inspiration. And so, which happens a lot at home. You do micro inventions to solve your everyday things. But these sustainable development goal issues are really, really big. But to actually start to solve the really big ones, so you need to just actually practice to get fluent in problem solving. So I don't know what actually your question was there, because I get too excited when we're so many great people trying to figure out stuff that I
Well,
don't really
maybe.
know. Yeah.
Well, perhaps we can actually try a solution together.
Yeah.
Because
Yeah.
I currently have an idea, but I think I want to maybe work with you on making it kind of come to life. And I think that I actually want to do something for Global Goal 13, climate action, really trying to understand how I can, really metabolize the problem and figure out a way that I can create a solution with like some basic, building. Would you like to help me with that, Eric?
I would. Let's try it. I've never tried it before, so let's do something. That's
All right.
I'm excited. Yep.
So I took a moment before this session, and I wanted to actually break it down by drawing. So kind of like a pseudo-coding exercise before I start opening into make code and start building with Strawbees and the robotics board. So currently we're using the robotic inventions board as part of our solution, using cardboard and paper as well. And I also want to use drawing as a way to kind of plan out my idea and kind of, inquire this process. So, I actually want to try to create a solution for a city. So I want to actually create a city where I want to protect against natural hazards. So, I haven't thought of a very specific city yet, but I was trying to think about the different types of natural hazards that are out there, like flooding, earthquakes, wildfires, droughts, and hurricanes. And although there is some controversy, or maybe there isn't full research on if climate change actually really directly affects earthquakes, I do want to include it as part of this process because natural hazards is something that expands into multiple areas. And I think I'm going to try and start by creating a solution for flooding, for areas that maybe are below sea level. So, I think, Eric, what do you think that I can do? So I'm going to actually just take my natural hazards and I'm going to quickly sketch out an idea of what I can do with microbit. So before I even start coding, just try like a pseudo coding. So like, for example, if I just draw, my friend microbit here.
It's blur.
Oh,
See the.
sometimes the camera just adjusts. Let's see if I can do this. Well, looks like it's a little blurry. So perhaps I might have to, just explain my idea then. So perhaps I'll just explain it briefly. So Eric, I think what I want to do perhaps is just switch back to my view. So, I think if we think about flooding, where there's like a rise in water that could be, it could actually be ignited by, a hurricane or, just melting ice caps that are, slowly making the sea level rise and rise. So I'm actually going to start by building like a city. So I have to my side like a city that I built, like kind of a basic model of a city. So I can actually use that to imagine the solution. So, if I have like a few houses at the very bottom of the city that's right next to the ocean, what do you think I can make to help when there is like flooding, perhaps maybe even from a hurricane?
Well, there's actually, when you talk about the hurricane, there's another way of measuring it. There's so many ways of, like, I know we've been discussing this a little bit before, but one thing, you would want to stop the wave of water, for example, like they do in the Netherlands or something. They have really massive walls that can stop. So you just need a good functioning sensor system to be able to raise those walls or barriers that can stop the impact from a wave. So I would do that. And then the thing is, what are you going to measure? And for pseudocode's sake, we can actually start looking at, okay, what are the sensors we have on the microbit? So original microbit, for example, we can use the built-in LEDs to sense light. So we could see that there's something happening when like a sensor gets covered by the water, for example. That's one way of looking at it. But that's a tricky thing because then it has to be waterproof and, there's another, it's a more tricky position. That at a certain level is going to be tricky. Another thing that I would do, I would put like these sensors that know the water level. And how can we make a water level sensor with a microbit? And maybe we should pose that question to someone else if you want to solve it, because immediately when you figure out, I want to use the tilt sensor in the microbit and sense the level of water, you can use a little bit of maths and one angle, and you'll know what the water level is. But then you also need to know it before it's too late to raise the wall. So where are you going to put that sensor? So there's so many problems to solve in a simple thing like that. But I would start by making a prototype. But when you said the hurricane, that it's going to be hurricane induced, we could even play with like at a certain level of wind sound. We know that it's actually on hurricane level. If you put the sensor, for example, the new V2 microphone inside of a sensor, you can know that now we're hurricane wind strength, because you can actually measure that if you design a system to do that. So, I mean, there's so many approaches, and this is a creative exercise to start with, just describing ways of using the sensors we have to measure something. For example, you could also just have like a circuit being closed by the water actually approaching, like in any point, the water will close the circuit because it will conduct electricity. So, I mean, now I'm stuck in this endless creative lateral thinking loop, because it's really fun to make a sensor to figure out when it's too, when a wave is coming, or where to put it. And so exactly, the exact same thing. So you see, this is when you have a system like the microbit, you have a certain set of interesting sensors that you can use, and there is that that boundary that to use the microbit actually makes you more creative in what sensors to use. So I saw that, I don't know if that happens at the same time there, but with the conductive value to detect water level is perfect. So that's one way of doing it. So, I mean, I don't know what you have been thinking about, Lindsay.
Yeah, I mean, I'm trying to think about using like a way to create a barrier. So like maybe a barrier to prevent like especially rushing waves, like also to give more time, because maybe that sometimes, you know, especially in a hurricane setting, you know, designing for that natural hazard setting, that it could be difficult to fully prevent the water from flooding in, but at least you can create a barrier that can, you know, provide the citizens of the city like more time to, you know, get to higher ground. But also, you know, maybe it's not like a lot of flooding. So, you know, this barrier could actually just help, you know, prevent flooding in like a lower area. So it's just like kind of a barrier to pop up. So, you know, maybe I can actually show my design, you know, so, and then we can kind of, you know, build off of that idea. So I've actually built like kind of a barrier, but maybe we can play with like the sensors or figure out a way to improve this solution, this invention. So
yeah.
See here. Yeah. So this is my very mini city. The small citizens, you know, in these little small houses, as well as a big tower up here. So this is like the higher level, but, you know, designing, you know, a solution for our citizens down here. So, you know, I have like my microbit set up, and I started by building this small little barrier here, you know, so it's actually see-through, but, you know, that way you can kind of see that it's, you know, see how it's like moving. And, but that way, if I put plastic or paper in here, I don't want it to actually harm the initial mechanical structure yet, but perhaps I want to, you know, just allow it to have like, you know, free range of movement, but I can also like change and modify it, maybe add cardboard or paper instead. But this is like a quick prototype that I can add here.
And I mean, that's the thing we want to, from my point of view in this, to actually get them started with, for example, invention literacy, like becoming like agents of and making change. They only need to be able to reach a level where they can describe what they are thinking around their prototype. They don't have to solve it perfectly, like covering it is irrelevant. It's just brute force because you might not have the time. But if you can think through a system that actually could be plausible and describe it with a working prototype, that's brilliant. So, I mean, great implementation.
Thank you.
Yeah.
So perhaps what was like the code that you were working on, you know, before we got started, like what I can, you know, add to this invention?
Sorry?
Well, you remember how we were brainstorming earlier about programming this? You had like many ideas. I saw that Mutaza also said connect 2 microbits with Bluetooth, one near the coast and the other city wall to trigger the wall and alarm citizens. So actually making an alarm system.
Yeah, which is also brilliant. The thing, this is what happens with the microbit. It's a very powerful device, and that's a great way of doing it. And then you have pair programming. So one is making the sensor system to figure out when a wave is coming. How do you separate that it's actually a hurricane with lots of waves from just a splash, for example? And then you can come up with another kind of challenge. And then it sends through radio faster, like the information to your barrier system, and then we raise it. So I don't know actually what approach. That's a great approach, and I think that a lot of students will also like stumble into that, which is a really, really nice way of yeah, and now, yeah, exactly. Warning systems that actually immediately light up before even the barrier starts.
Oh yeah, so it actually could be even just signage. So it doesn't actually have to be a barrier, but it could just be a sign where maybe it flashes orange, or
you can have a combination. Like there's this big wave, there's the lights on the microbit, and the future microbit, you can also do sound. So I mean, this is the thing. This is a great way of exercising it. And if you give them the challenge, lots of students will come up with different ways of solving it. And that is the power feature of all of this. It's like they make mechanical sketches, they make just the code sketches. They make, so we have the lights, the 2 Neo pixels on our robotic board, which can also light up. And then you could have used the microbit LEDs to signal a certain level of strength, for example. There's so many ways of approaching it. I get very inspired by the comments. So
Well, Eric, let's try a basic pair programming. Perhaps you can share your screen and show us, how you would code it.
Oh yeah, I haven't even thought about this. So let's see if I can see if I can remove the previous code. So let's see if I can.
Yeah, and then I'll try.
So how share my screen? There we have it. Share screen. Wait. Point. I gave your project a name. So let's say, we call it flood barrier.
Yeah, flood barrier.
Wait, with an E, with the 3 as an E. So I'm really fancy. That was accidental, which is because they're very close to each other. So I'll do it just because I'm with it. Let's see. And it's creating a new project. I don't think it's ever been that slow for me before. So there's lots of ways of approaching this, of course. But let's say that we, for example, use the clips. Then we have to just figure out the input and what's the input we want to use. So for example, is this the pin, that's the pin pressed, pin P, that's a closed circuit. We could read the level also, but for example, if we would measure the water level, this could be using the crocodile clips. And obviously this will be a lot of people showing lots of solutions for this, but this is one way of going about it. And then we think, okay, what is going to happen once this P0 is pressed, which would be the crocodile clips going into the water. So Lindsay, what do you think we should do there?
Ooh.
Should we raise the gates immediately, or should we do like the others? Can we like measure a level of conductivity, for example?
I think measure a level of conductivity.
Okay, and what do we use then? Then we use the input. Do we have a nice measuring of the these levels, how much they are? Does anybody have that in? So I haven't used that. So let's do, instead of, for example, doing, let's use the angle. Oh, that's rotation. I'm going into the more thing here. Let's go for a simple acceleration. So, and now I really need to think. So the y-axis is what, if you have your system there, and we imagine that we have something, this is somewhere out in the ocean, and it can float or like tilt on the back end and tilt up when water comes, or the water level rises. Can you show no, I can't show. Can I show myself here? You see me here.
Yep, we can see you.
On the little screen.
Yep.
So what I'm thinking, just to keep it simple, maybe we could just use it's standing like this, normal mode, And then you have a pretty big signal, a negative, probably, what's it, minus 1024. So we're not quite on the full negative G here. But you're tilting it up, you'll see some difference. And then you have to just figure out what's the value where we need to sound the alarm, or maybe raise the different alarms. So I don't know how complex we should make it here, because this is
I think for the sake of time, keep it simple.
Okay, so then we'll try to use some logic. So let's say we just have a simple if statement here. And now I actually don't even remember exactly what the microbit says there, and I'm not use too many different systems. So let's see if we use a this little logic thing. So when acceleration y is smaller than, so anybody in the comment section knows exactly, it's 1024, which is what they use. So maybe it's when what's the level. I would actually do a measuring device first to see what are the levels we get are and what I want to calibrate it. So I would actually make a calibration device first, but I won't be able to do that now. So I'll put the system out in the open, and then see this level is where I need to go to level 1, and this level is. But for now, for simplicity's sake, let's just use well, the absolute. I mean, smaller or bigger than. Because if we're negative, then it's bigger than minus 500. I think it's a negative value when the microbit is standing up. So I don't know exactly. So this is somebody, you can all correct me here. So I'm just coming up, let's go higher than minus 500 or something. Does anybody follow how those things work? And then something should happen, else it can be down. So let's say we have...
Eric, they say, Chris says, use a number block to get a readout on tilt.
On tilt, yeah, from the more. Yeah, so you can do a readout, but wait, let's just, for now, we can do a sample, just keep it really, really simple. This will, at a certain level, we'll see that it's like, it should be able to work, but maybe I could do that too. But I'll just put in the straw. Oh, then I need to search for our advanced stuff, because now I have started. Now you see how to find the Strawbees robotics. I need my Strawbees blocks to be able to move the wall. And
good ideas, Chris. So I really like this coding session, because this is actually a nice way to include a team to collaborate on an invention, especially in a session where we are still doing remote learning experiences.
Yeah,
I'm really enjoying this pair programming, try coding.
Yeah, maybe we should. Maybe I can open the chat, because I'm like out in a completely different window here.
Well, just keep going.
Okay,
we'll tell you.
You know, so we could use the tilt variable. We could put it in a variable or do a read. Now we're just doing a very, very simplest way of just getting something happening. So on a certain level, the servo A will move from position, whatever position it's in before that, to 100%. So I don't know exactly how your servo is put. So that's also something you would test. And if it's not there, we can have the servo position on a closed. Now I'm using transition servo, but that's also trickier possibly than using the other. So let's go from now it's going to be switching back and forth depending on how this is moving. So it's all about calibrating the sensors and knowing what your microbit can see. So I would just do tests of this very simple code. And then I would also do the radio transmission, for example. Instead of, if this was just the sensor microbit, it could, instead of moving the servo, it would send a signal saying raise the gates, or like raise to level 1, 2, 3 alarm level. So, but all of those things takes a bit more time to do. So I would just do a very simple, fast, quick, and dirty solution here. And I don't think 100%. Maybe you if I see it, it's right angled. You want to move approximately 90 degrees, and that would be maybe a 60% or something. 70, I don't remember exactly how it is on this one. So something like this would do the very, very basic level of sea level raising up. Then you just calibrate when you want it to activate, and it should only be able to go in between these levels because you're locking the microbit mechanically in your system there.
Mm-hmm.
So that's one way of doing it. Very, very rough. And on start, you could also put the servo position at, let's see, so I could take my servo position to down, which I don't know now if it's down or up, 0 or 70, but I'll say that 0 is down, and then you put your system to whatever it actually does when you test it. And then I would also suggest, like what I always do when I do this, I even have another signal. So usually I do, to be able to do my calibrations and make my robots, test my robots, I have a second block always on the start for 50%, so I know where the center is, and then I have it offset, and then I can actually do some calibrations of where the movement's going to be. So I have some calibration servos just in the beginning. I don't know if you follow that, but it's my way of doing my quick modeling. So yeah, that's an example of I don't even know if this would work, but if
Well, why don't you try the virtual microbit? So test it on the actual virtual simulator.
Oh yeah, you see the value there. Yeah, look.
There you go.
So it what's actually, I don't know, this is simulating that it's, actually don't understand what the tilt is. Is this laying flat or is it standing up?
I think now it's tilting back.
Yeah, yeah, that's what I'm thinking. But if it's, so when it's flat here, it is, because I'm sorry for feeling so confused about this, but I haven't been using this for quite a while because I'm doing a completely different set of code right now. So let's see here, there, AY0, and that means that it's giving us, what's the position of the servo in real life then? Is that when, or the microbit, is that when it's standing like this?
Mm-hmm.
Then my approximation was wrong, because then it's going to be when it's rising up like this. So then you would actually want to when it's lower than minus 500, you would shift that. But that would just be a way of testing it. So you'll see that something happens when you move past a certain point.
Well, let's try it in real life.
You see?
Well, let's apply it to our prototype here.
Can you put that in there, or should I share it with you? Or
no, I got it. So just stop sharing your screen, and then I'm just going to show it in my example.
I'll stop my share.
No problem. So I'll just pin my screen so we can watch it for a moment. Yeah, so I was coding along with you.
Oh yeah, perfect.
So I might have to fix the position of the servo motor.
Yeah, that's one of the things. So if you, for example, now just test it on the servo point B, you'll see what 0 is, or like 50%, which the center.
Let's see. Make sure. So this is the end. So then, so about here.
Depends on what 0 and 1 is. So that's why I was saying if you test it on if you connect servo B to the servo to B.
That's right. That's right. Because I set up on C ahead of time.
And then you do it to servo A. Did I even choose? I think I was on servo A with the
servo A.
Yeah, servo A is where
there we go.
Okay, and now you can just shift the arm till it, because now it's in a 0 was the wrong direction, most likely.
Okay.
Is it?
Yeah, so this is the end. So now it's all over.
But do you see, do you get the servo to move if you do that tilting thing? It doesn't look like we didn't use.
Well,
but it is.
I think it's okay. So I mean, ideally, we'll just you know, because we're running low on time, so that's okay. But I think for now, like, you know, ideally the idea would be to, you know, have the barrier down, and then it would go up.
Yeah, so that was 0 position down, and then so you could also just send a 0 on the B. But okay, well, it's interesting. And now it's connected on the A.
Yeah.
And it has batteries and it's on.
Yeah, but that's okay. So, I mean, ultimately that was like our idea. So of course, like, you know, getting it right the first time, that's kind of very rare anyways. So this is part of this process that we wanted to show. So we'll after this planar, we'll fix the code and share our example afterward. So, you know, now we're starting to reach the end of our planar, but I just wanted to show like a really simple process of how to use kind of like the robotic inventions board, but, you know, ideally just, you know, building a really simple prototype and, you know, going through a process, but also giving you ideas to bring back to your students and how you can kind of implement this process, especially over Zoom, as well as the resources that you can use to implement. So all of this activities we actually have on Strawbees Learning. So I'm just going to go ahead and share my screen so you can see the last bit of resources, and then I'll start to close the session.
Oh, I wanted to show the radio crane. I can do that later. Because that would actually solve the same problem. It actually uses the radio transmission. So you'd have the little sensor out in the water and then you move the crane immediately with the water. So, but let's not do that. We'll show that on video
well,
later.
Why don't we actually you know, share that after? So we'll share our resources, fine tune them, fix them up. So I want to point at a few resources that we have also to you know, pass out to your students. We have coding cards, so small snippets of code that you can use that's on MakeCode, as well as Strawbees Learning. I have you know, presented all the slides and put it in the chat, so you can actually use the resources, and there's a large group of links at the end, so you can refer to the locations where the coding cards are. And I even put a few extra examples just for more inspiration to think about, especially for the different global goals 3 and 13. So Eric has made this great hand washing counter. So it's basically using the World Health Organization's 40-second hand washing routine. And he kind of used the microbit to, you know, create a switch where you can, you know, complete the switch, turn on basically the hand washing counter using your elbow. So without using your hands, you can just use this as a 40-second counter. And then, also we have, you know, our great ambassadors, Abby and Sam Yancey, that have created a grabber. You know, so this was a really excellent example of an invention made for Global Goal 3, which is like basically being able to pick up litter and picking up things, objects that are out of reach. So this is another implementation of actually an activity that we have that we didn't originally make for the microbit, but they remade into this grabber claw. So it's a fantastic tool to think about accessibility needs. And then the example that we just, you know, shared now. So we'll give you the code and a few bits of extra information about the shake table as well. And so I think we have now reached the end of our planar. That actually went fairly quickly, much faster than I thought, but I hope everyone had a great time, and, you know, feel free to share your ideas. So of course you can go to Microbit's website and go to the Do Your Bit site to submit your submissions for your students, as well as share. So, you know, there's a large group of handles on Facebook, Twitter, LinkedIn, and also using the hashtags, #microbit, #globalgoals, and #strawbees. So if you create something, we want to see, share your ideas. We would love to see as well. And then also, as I mentioned, we also have a large link of resources at the end. So feel free to look through and use it as a way to help you get started. So I'm just going to go back here. Excellent, excellent. So thank you everyone for joining us for this this great session. I hope everyone had a great time, and you know, appreciate the help also in the chat, giving us some examples and ideas to code and keep it going. But again, please share your ideas. Thanks again. All right.
Okay, bye.
Take care.
Take care.